Hello, my name is Parth, and this is my lab 4 for bar magnets. So the purpose of this lab is to measure how the magnetic field of a bar magnet changes with distance using a photomagnetometer. We'll use this experimental data to find the magnet's magnetic dipole moment, mu, and then plug that value into a closed group code to build a computational model of its field. The final goal is to test our model's accuracy by comparing its prediction for an off-axis measurement to a real value we measured in the lab. So some assumptions to keep into consideration. So we want to make sure we're assuming that rotating the phone to Bx equals 0 successfully isolates the magnet's field on the x-axis, separating it from the Earth's field on the y-axis. So we're basically isolating the Earth's field. Next, we're assuming an ideal dipole model where we assume our real magnet act like a single point like dipole, as all of our formulas are based on this ideal model. We're going to assume no stray fields. We assume our workspace is clean and that no other electronics or metals are interfering with our magnetometer readings. So first, we'll create an experimental model by plotting our measured ln bx versus lnr data, where the slope will be our distance dependence n, and the intercept will give us our magnet's magnetic dipole moment mu. Next, we'll plug this experimental mu value into closed group computational model that uses the Bio-Savart law to visualize the 3D magnet field. The final goal is to test our model's accuracy by comparing it to 45-degree field prediction to our actual off-axis measurement from the lab. So the preview of the main result. The experimental data confirms that the magnetic field decreases as the distance from the magnet increases. The result also shows that the magnetic field on the parallel axis is approximately twice as strong as the field on the perpendicular axis at the same distance. Distance dependence n is negative 1.2657. The constant k is 8.073 times 10 to the negative 6, and the magnetic moment mu is 4.773 a times m squared. So some fundamental physics principles. So our magnetic field due to a bar magnet this is our magnetic field versus our distance. This is the first formula right here. This is our experimental model. We plot it in its linear form, which is this formula right here, where the slope is our n and the y-intercept gives us the k constant. Now this formula is the on-axis B field. This is the simplified theoretical formula from the magnetic field only along the dipole's axis, showing the field decreases with 1 over r cubed. We use this to connect our experimental k value to the magnet's strength mu. So third formula right here is the Bio-Savart law. This is the complete vector formula for the dipole's magnetic field at any given point in the 3D space. We use this complex formula in our closed group code to create a computational model and calculate the field off-axis. All right, so this is the setup. Firstly, we're going to define the system and the surroundings. The system consists of the phone and the magnetometer. The surrounding consists of the Earth and the bar magnet. These images right here, they show in sequence the setup of our experiment, which I'll go through right now. We first want to find the magnetometer sensor, so we locate the magnetometer chip, sliding the phone over the magnet and marking the x of the maximum Bx and By fields 1. We compensate for the Earth, so we rotate the phone magnet far away until Bx reads 0, 2. This aligns the setup to isolate Earth's field on the y-axis. So then we take on-axis data, place the magnet on the east-west meter stick, and then we slide the phone sensor along the stick, recording the distances r that produce Bx fields of 2070, 120, 170, 220 mu t. Then we take off-axis data. We find the distance d perpendicular. That gives us the net B field of 100 mu t. Move the phone to the d perp location at the 45-degree angle. Record the Bx, By, Bz values, and correct the measured By values by subtracting Earth's magnetic field. So this is our setup. These are experimental conditions. So the linear fit is the ln bx versus ln r graph, and this is what we got. Y equals negative 1.2657 times x minus 11.727. The distance dependence n is negative 1.2657, and the magnetic constant is this value right here. The magnetic moment, so mu, is 4.773 a times m squared. And so the observation is that the bx field increased as the magnetometer moved closer to the magnet and approached 0 when it moved far away. So these are our values. These are just what we use to compute the experimental values. This is our closed group code. I have snippets right here to show the main code, and on the right here is our results, what we got, and to compare our experimental values to our computational values. So this is our experimental values, which yielded us the vector negative 1.73 times 10 to the negative 5, this one right here, and it had a magnitude of 9.857 e to the negative 5. Our computational model yielded us a vector with this magnitude of 3.014 e to the negative 5. So our computational model was yielded us a smaller magnitude value for our B field. So some possible sources of error. So we could have had measurement inconsistencies. It was difficult to read the exact distance r on the ruler at the precise moment the bx value hit its target, and so this could probably create some sort of skewed data in our plot. And next is there's too much movement. The 45-degree measurement was very sensitive to our phone's orientation, and so even any slight tilt would have caused the sensor to incorrectly read the B field's components. And I think nearby electronic devices, even maybe that we had not considered previously, so aside from our phones,